Today we will discuss the two component system. Generally, in a two component system, we have the rule that is a degree of freedom is equal to C minus P plus 2. Okay, therefore, in two component system, C is 2 and if phase is present 1, then degree of freedom will be is equal to 2 minus phase is 1 plus 2, therefore is equal to 3. Okay, two component system and phase is 1, then the degree of freedom for this system is 3. Therefore, 3 means we required for description of this system temperature, pressure and concentration. Okay. By using these 3 variables, we can describe this system. Okay. Therefore, 3 variables means you should require the 3 coordinates, that is x, y coordinates, then x coordinate and z coordinate. Okay. Your phase diagram can be 3 dimensional, and therefore it is difficult to understand this 3 dimensional phase diagram. Then practically, when you have the two component system and it is having the alloy like the Ag and Pb, lead and silver, when you mix, then our boiling point of Ag is more than 200 degrees Celsius and boiling point of Pb is more than 1600 degrees Celsius. Okay, this is the round figures I have given, not exact boiling points. Okay, silver is having boiling point 2000 degree, more than 2000 degrees Celsius, and Pb is more than the 1600 degrees Celsius. Therefore, their boiling point is much higher. Okay, and we have studied the melting point curves of these two alloy. Okay, therefore their boiling point is higher than vapor phase practically absent in this case. Okay, when two alloys is mixed, because it requires a very high boil, their boiling point is higher, and at the point of boiling point, then these liquids are in contact with the vapors, and there is vapor phase will act. But before the boiling point, the vapor phase is practically absent, or if it is absent, if it is present, then very low vapor phase you found for these cases. Okay, therefore, when you consider the pressure and when gas is there, gas is strongly affected by the pressure. Okay, if you compress, the gas volume is changed. If you then expand, gas volume is changed, but pressure will not affect as more, which affects in gases, in a solid or liquid phases. Therefore, in this case, we can neglect it, because here vapor phase practically absent, because the boiling points of these Ag and Pb is the higher. Therefore, vapors is not there, gas phase is not there, therefore pressure is not affect the system. Therefore, in this case we can neglect it, and all this process we can carry out at constant pressure. Okay, this all the things we can carry out, this all the diagram we will discuss under constant pressure. No variation of pressure we use in this case. Okay, therefore at a constant pressure, this phase diagram of the two components can be possible to using the diagram which is having temperature and composition diagram. There is a temperature at one side and the composition at other side. We can use this two-dimensional diagram and can give the explanation for the this type of phases of the two component system. Therefore, we have reduced the pressure for this system, and we done this process or the phase diagram under constant pressure at 1 atmospheric pressure. We done this all these things. Then our degree of freedom rule or Gibbs rule can be reduced as C minus P. Instead of 2, we used 1 at this place. Okay, this is the reduced Gibbs rule or phase rule. Gibbs phase rule. This is called as the reduced Gibbs phase rule. Okay. Why we use this reduced Gibbs phase rule? Because one of the less important variables. Okay, in this case, pressure was a less important variable. Therefore, we remove the pressure, and at a constant pressure, we vary the composition and vary the temperature. We have to discuss this diagram. Okay. Now we have discussed about the why we use the reduced phase rule and when we neglect the pressure. Okay. Or at a constant pressure we do this, neglect pressure, and we are studying at the constant pressure. Then this system is the condensed system. This is called as a condensed system, and reduced Gibbs rule or condensed Gibbs rule. Sometimes it is also referred as a condensed Gibbs rule. Condensed Gibbs rule means we neglect the pressure, we neglect the less variable, less important variables. That is, pressure is less important variables in this case. Therefore, we have neglected the pressure in this case. Now, what is meaning of the actual diagram of this? We have to discuss. Now, here silver. At that point, you found that, okay, we have a jar, and in this jar only silver is there. Okay, and you heated it at 961 degrees Celsius. Okay, therefore there is it melts, and there should be a equilibrium. Okay, during the equilibrium there is a liquid and solid equilibrium you find during the melting. Okay, at this point 961 degrees Celsius, 961 degrees Celsius is melting point of silver. Okay, therefore at silver, only silver is present. Okay, at that point 100% silver is present. It means only silver is present on this coordinate. At the first, when you start the experiment, only silver is there, and you heated this silver 961 degrees Celsius temperature. Our silver shows the melting point. Okay, that is also, this is also the freezing point, and this is also the melting point for the DCG. Okay, that curve. Okay, that is we given the name A, C, and B. At the A, okay, at the point A, only Ag is present, and it is boiled at a 961 degree Celsius. Okay, when you as we now as the coordinate proceeds forward, we are adding the Pb to this mixture, to this silver at that up to this point, and you found that as you add the silver up lead to this, okay, where we add the lead, okay, the second we add the, at this point there was the only Ag is present at 961 degrees Celsius, there was only Ag, and when you add at that point, okay, we added the Pb externally to this system, okay, then its boiling point, its melting point decreases, okay, on the through of the AC. When you are going to add the Pb, okay, you are adding at every point, you are adding, okay, you are adding at that point the Pb is the 50% you obtain, 50 and 50% you have the Pb and Ag, okay. As you added the Pb to this system, the melting point or the freezing point of this silver goes on decreasing, melting point goes on decreasing up to the point C, okay. Now at the second point, when you have at this B point, you have the only Pb, that is the lead is there, and lead is melted at 327 degrees Celsius. Okay, at this system you found there is only Pb 100%, no addition is there. Okay, okay, at this point you are melted, Pb is there, and solid liquid is there, and it is melt at 327 degrees Celsius at that point, and only 100% lead is present. As soon as you added the silver to this, okay, at the 100% Pb, then its melting point goes on decreasing, or its freezing point goes on decreasing. Okay, this is a freezing point curve. Okay, BC is a freezing point curve. BC is a freezing point curve or melting point curve. Freezing point curve BC of Pb. BC is a freezing point curve of Pb, and this curve is a freezing point curve of Ag. Okay, this curve is the freezing point curve of silver. Okay, now you got the idea. You add the after the addition, when you add the in silver the lead, then also its melting point decreases. Okay, depression in melting point or depression in freezing point takes place, and again in this case when you add the Ag, then its melting point also goes on decreasing. Okay, this is the very briefly we discussed the diagram or phase diagram of the two component system, that is Ag, Pb. Okay, now we will discuss how many phases present in this two component system. Okay, we are summarize how many phases is present in this system. Okay, here Ag solid is present at this point, and plus solution of Ag and Pb is present. Okay, solution of Ag and Pb is present. Okay, here is the Pb, solid is present, and solution of Ag plus Pb. Okay, solution of Ag plus Pb is present, and here Ag solid is present, and solution of Ag and Pb is present. Okay, during this line. Okay, at the below there is solid Ag and Pb is present below the 303 degrees Celsius, and at that point also solid at C, solid Ag present, solid Pb present, and also molten or solution. Okay, instead of molten or solution of Ag and Pb present. Okay, the solubility of Ag in Pb is very small. They can mix at a particular temperature, but not very much they mix. Okay, their solubility is less. Okay, they soluble to each other is the less in quantity. Okay, now we will describe the first area, that is the ACB. the area ACB. Okay, above ACB, you remember that, above ACB, you have only miscible liquids is there. PB and Ag are the molten solution. Okay, molten solution of PB and Ag. Okay, above this region you can find there is a molten PB and Ag mixed thoroughly, and therefore at this stage there is only one phase present, because when solution is there, okay, this is liquid solution, when solution is there, then we consider that solution as a single phase. Okay, at this case there is a single phase is present during this big area. Then we have the reduced phase rule. Okay, therefore reduced phase rule is given as C minus P plus 1. Okay, this is the reduced phase rule, because one variant pressure we have neglected, we have not used the pressure. Okay, there is 3 degree of freedom is there when we consider only one phase is there. Okay, you found that there in this case Ag is solid Ag, one of the phase is there, then solid PB is one of the phase is there, and the solution of PB plus Ag, one of the phase is there, and vapor phase is, okay, 4 phases is present in this 2 component system. But we have at its boiling point of the lead and silver is very high, therefore we neglect the vapor phase, because the boiling point vapor when arises when the boiling point is there. Okay, boil, if your solid or liquid boils, then vapor is arises. Okay, in this case the boiling points of the Ag and the boiling point of PB is very high, therefore practically vapor phase is not present. Therefore the third coordinate, vapor phase or the pressure, we have neglected. Less important, it is less important variables, that is pressure we have neglected, and we have derived and described this phase rule. Okay, now the system, in this system only one phase is present. Component is, no doubt there is a 2 component PB and Ag is there, 2 minus phase is present 1 plus 2. Okay, 1 plus 1, therefore system is bivariant. This area is a bivariant. Okay, during this there is a bivariant. Okay, the area below AC, okay, this area below AC, okay, area below AC and BC, area below AC and the BC. Okay, now the area below the BC, there is a Ag is a solid. Okay, for a solid we have the rule, for a solid one phase is considered. Then silver and the PB, are in solution, therefore Ag plus PB is the solution. Okay, solution, for a solution we consider a single phase. Okay, therefore by summation of these, there is a 2 phase. Okay, at the area below AC there is a 2 phases present. Therefore degree of freedom for the region below the AC is equal to given by that is the freedom, that F dash. Okay, normal, this is not a normal degree of freedom rule, this is the reduced degree of freedom rule. Okay, instead of 2 we have used only 1. Therefore C minus P plus 1, component is the 2, therefore phases is the 2, therefore 1. In this area our system is a monovariant system. Remember that our system is a monovariant system. Remember that in this area system is a monovariant system. Okay, area is big. Okay, according to we discussed previously, if area is big, system is the bivariant. But when system only one phase is there, then we consider the system is bivariant. In this case it is a monovariant Same we have applied to this. Okay, there is a PB is a solid, therefore one phase. PB plus Ag is the solution, one phase, therefore two phase system is there. Component is the 2, therefore 2 minus 2 plus 1, therefore it is also monovariant system. This system is also monovariant system. Remember that. The area below the BC is also the monovariant system. Now, the area below the temperature 303 degrees Celsius, you found that there is a two phases. Ag is a solid and PB is also solid. Okay, it is not a single phase. If it is single phase, big area is there. According to our tricks, we can say that there is this system is the bivariant, but there is a two phases is present, like that. There is two present, there is a two phases is present, but system we can consider as a monovariant. We found the system is the monovariant. The area below 303 degrees Celsius we can describe like for this Ag is a solid and plus PB is also solid. Therefore, there are two phases present. Therefore, for this system, degree of freedom will be is equal to C minus P plus 1. Therefore, C component is 2, phases is 2. Therefore, one system is the monovariant system. System is a monovariant system. Okay, this system is a monovariant system. This is also monovariant system, and third is also monovariant system, and this is the bivariant system. This is called the bivariant system. Okay, the area we have described. Therefore, the area, first area we have described, then the second area we have described, then the third area we have described, and the fourth area we have already discussed. Now, we have to describe the curve AC. Curve AC and curve BC. Okay, there are two areas we have to describe. During this curve, you found that there is also solid Ag is present and also liquid PB plus Ag is present. Okay, there is equilibrium between solid Ag and liquid PB Ag is present. Okay, at the side Ag solid and at the side liquid PB. Okay, both phases is present during this curve. Okay, during this curve you have the Ag solid. Okay, we consider this. Okay, during and from this one phase is consider this, and second phase is consider during this. Okay, this line is made up by this phase and this phase. Okay, therefore this line consider also Ag solid plus Ag plus PB solution and also liquid PB. Okay, when and the same, this is the one and the same. Okay, when Ag plus PB solution, Ag plus PB solution, it is the one and the same. Therefore, the Ag solid and PB plus Ag along this line is a solution, and therefore it is considered the one phase and solid is considered the one phase. Therefore, two phases is present along the AC. Therefore, degree of freedom F dash is equal to number of component 2 minus phases 2 plus 1. During this, it is a monovariant system. Remember that. This system is a monovariant system. Along the AC, the system is a monovariant system. Remember that. System is a monovariant system. Okay. Same we use for this BC. Okay, for the BC, there is a PB is a solid and also Ag plus PB solution is there. Okay, in this PB is the solid, Ag plus solution is, and equilibrium with the liquid PB. Ag plus PB is the same, therefore it is one and the same solution, and PB is a solid. Therefore, for this one phase and PB solid one phase, two phases present. Therefore, degree of freedom for this is equal to 2 minus 2 plus 1. Therefore, 1. Degree of freedom for the line base is equal to the monovariant system. Along the BC system is the monovariant system. Remember that. Now, very important point we have to discuss, that is last point, that is the C. C point is called as the eutectic point. At that point, when you take the 97.5 PB and 2.5 Ag, that is a silver is there, then this point is arise. This point is arise at the 303 degrees Celsius temperature, and the composition should be 97.5% Pb and the 2.5% Ag. Okay, now at this eutectic point you found that there is a solid Ag is also present, solid Pb is also present, and molten Ag plus Pb also present. Therefore this system is three phases present in this system. Solid Ag is present and solid Pb second phase is present and solution is there. Therefore there are three phases present at the eutectic point. Then therefore degree of freedom by using the formula C minus P plus 1 is equal to, in this case component is no doubt our two component system, 2 minus phases is the 3 plus 1, therefore 2 minus 3, therefore minus 1 plus 1 is equal to 0. Therefore that point is a non-variant point and the zero variant. If you change the composition, the point is there is no such kind of equilibrium is observed, no solid Pb and no molten, that equilibrium is observed when you change the composition. And when you increases the temperature, also equilibrium is disturbed. When you increase the temperature, there should be only liquid and Pb is present at that point. And when you decrease the temperature, only solid and Ag Pb, only solid Ag and Pb is present. Only at the point C, you found that there is a solid Ag is also present, there is solid Pb is also present, and molten Ag solution, Ag plus Pb solution is present there. Therefore, this system is a zero variant system. At the C, system is a zero variant system. Okay, this is all about the two component system. Okay, I hope you got all of this. You get the idea what is the two component system. Thank you very much.